Hi, Nick McQuaid here with the second video of day 13 of iste780, Data-Driven Knowledge Discovery. Today, in this recording, I'd like to talk all about splines, and it looks like a lot of stuff here. Regression splines and smoothing splines are really the two topics, and all of the other topics shown here are really just subheadings. So let's get started. Now, before we talk about splines, let's talk about the opposite of splines. Let's go way back to chapter 3 and a concept called interpolation. So here's an example of interpolation. This is a curve that fits every single data point perfectly because it passes through every single data point perfectly. And we could call this curve very jumpy or very wiggly. And this is the training data. So we can also call this an example of overfitting, because this fits the training data so well that there's very little chance that it's going to fit any kind of test data. It's overfit to the training data, and it's overfit by interpolation. But interpolation accomplishes something. Let's go even farther back here to here. What we're trying to do in fitting a curve is to minimize the deviations of the points from that curve. So here is an example that shows a linear regression curve and the distance between every point. So we're going to take the square of this distance and sum up all of the squares of these distances and try to minimize those. And in the case of linear regression, we're constrained to trying to minimize those with a straight line. So the straight line is quite smooth. But if we're not constrained to do that, as we're not with k nearest neighbors, and we pick a particular value, we can get a wiggly, jumpy, overfit line that passes through every training data point. So there's a fundamental tension between trying to minimize these deviations and trying to get a curve that's smooth enough that it has some hope of fitting the test data. And we looked at splines. So let's go back even further here. I think it's in here in chapter 2. This is a key picture where we looked at a spline. This isn't quite interpolated. A spline is a special kind of curve that is constrained to be smooth in a certain way. That's what a spline is, a curve that is constrained to be smooth in some kind of way. And so this spline curve is smooth in comparison with the interpolation that we just looked at with the k nearest neighbors. But it's still pretty jumpy, it's still pretty wiggly. It's not too constrained. So one question would be, how do we constrain a spline so that we can make it somewhat smooth? As a matter of fact, I think both of these are splines. I think the blue one is let's just take a look here. I think the blue one is a spline that's just more constrained. Let's see, smoothing spline fits blue and green curves. So you can see that the blue line is much smoother than the green line, and yet they're both smoothing splines. So we're going to talk about splines in this section. So let me go back to section 7 point, whatever it is. Where are we? Chapter blah, regression splines. So the first method that we're going to look at is going to be regression splines. And this is another example of basis functions. So we looked at basis functions in the previous two sections, and the idea was we plugged some function into here. And we're going to do that here. The difference with regression splines is we're going to mix up a little bit of the step function idea into it. So here we see a regression formula that's a cubic polynomial. So a cubic polynomial by itself isn't good. So here's an example of a cubic polynomial. If we just fit a cubic polynomial, we might get some horribly discontinuous thing like this. So we fit a cubic polynomial to part of the curve if x is less than some constant. If x is greater than some constant, then we fit a different cubic polynomial. Okay, and we estimate the coefficients of those two polynomials, or those k polynomials. We may have more than two categories. This is just an example. But and the way that we talk about the categories here is with knots. So that's a term that's used in this textbook. You may, if you've encountered splines before, you more likely have encountered the term nodes. So splines change at nodes. So this is a node right here, a discontinuous node. Here's a node that's continuous, but it's not really very smooth. Here's one that's quite smooth, and here's one that's smooth in linear terms. So this, I should say, this one was smooth in cubic terms. So this is most closely what we're trying to achieve with this situation here. So what we have is two different cubic polynomials, and so we can call them together. We can call them a piecewise cubic polynomial, and it has a single knot, so there are two of them. If it had two knots, there would be three of them. In other words, there would be three categories, and so on. So the number of knots is obviously very central to this. And another idea that's very central to this is going to be how we get the smoothness. So for regression, this is the formula that is used. You don't have to apply this directly. You'll simply have R apply this. You'll use what's called a truncated power basis function. So this function will take on a certain value, and what's important about that value is that it is continuous for the first and second derivatives. It's only discontinuous at the third derivative. And that makes it more smooth. So if you haven't done much math, the concept of derivatives may not be familiar to you. But if you have done it, then you know enough probably to do the mechanics of this. But essentially, this is a way that we can use math to sort of define the amount of smoothness that we want. There's actually a good kind of non-mathematical description for smoothing splines, better than the one for regression splines, which we'll get to in a minute here. In fact, let's just go on. Let's see. Okay, so we have to choose the number of knots. This is something that R can help us with. We can choose, we can let R choose automatically number of knots. And here's a cubic spline fit to the wage and the wage data. And using, I think this is the one that uses 4 knots, or 3 knots, so 4 categories. I think there's a knot at each vertical line here. Oh, and here's the equivalent, what we saw in the previous section of the logistic regression of age. So we get smooth fits for these curves, and blah blah blah. So let's so this is superior to So we looked at polynomial regression. This is superior to polynomial regression because we get a lot of flexibility without high degree. The high degree gives us a lot of craziness. So we get a lot of flexibility and stability. So this is kind of a superior approach in general to polynomial regression. But I want to move on to smoothing splines because I think the explanation is more natural for. In fact, I might have even put smoothing splines first in the chapter because I think you can understand the regression splines better if you understand the smoothing splines. So here's a discussion about this trade-off that I mentioned, and this is exactly how we can deal with this trade-off. This is the trade-off between minimizing the deviations, which is what this is trying to do, and getting a smooth curve, which is what this is trying to do. So this approach, if we can minimize this expression here, we get both minimal deviations and a smooth fit. And the key is that we use this tuning parameter, just as we've used a tuning parameter called lambda in other contexts. we use this tuning parameter to determine how smooth we want it. The larger the value of this, the more smooth it's going to be. Now, if you haven't done too much math, the idea that this is the integral of the second derivative may not be familiar to you. But that's okay, because there's a pretty much non-mathematical description right here. And this was equation 711. So here's the description. Let's see where it starts here. Yeah. So this is a really concise description that doesn't require math. If g is very smooth, that is that function. If that function is smooth, then its first derivative, that's g prime of t, will be close to constant, and the integral of g double prime of t squared dt will take on a small value. Conversely, if g is jumpy and variable, then g prime will vary significantly, and the integral of g double prime t squared dt will take on a large value. Therefore, the tuning parameter lambda times the integral of g double prime t squared dt encourages g to be smooth. The larger the value of lambda, the smoother g will be. Okay, so we can let it be jumpy. And if you think back to the picture I showed you at the beginning from chapter 2, where we saw the green smoothing spline and the blue smoothing spline, you can probably guess that the blue smoothing spline simply had a larger value of lambda specified, and the green one simply had a smaller value of lambda specified. And if lambda is 0, then the penalty term has no effect, and so the function g will interpolate. So this is the worst. This is exactly what we saw when we looked at the k nearest neighbors example from chapter 3. Okay, so now how do we choose the smoothing parameter? Well, we've already learned that. Basically, we're going to use cross-validation to do that. Now, there is one concept here that's kind of odd that I'm pretty much willing to bet that most of you have had at least enough statistics that you think of parameters, you think of degrees of freedom as referring to the number of free parameters. So it says here, usually degrees of freedom refer to the number of free parameters. And here we're going to see fractional degrees of freedom, so that's going to seem really odd. And the reason for it is this. We have this equation that you don't have to worry about. You don't have to actually do anything with it. But this equation leads us to the idea that the degrees of freedom can be expressed as the sum of the diagonal elements of a certain matrix here. This expression here says sum, and the curly braces say the element of, and II means the elements along the main diagonal. So that's element in the first row in the first column, the second row in the second column, the third row in the third column, fourth row in the fourth column, and so on. So those elements are not integers. The result of this equation is going to be that those elements could take on fractional values. So the sum of those fractional values will be the effective degrees of freedom, and it will be in our example here it'll specifically be a non-integer solution. So let's take a look at the example that's given here is two curves, one with 16 degrees of freedom and one with 6.8 degrees of freedom, using leave one out cross-validation. So we've already learned that. And you can see that with more degrees of freedom, the curve is more wiggly. And the point that is made here is that choosing the smaller degrees of freedom obeys the principle of Occam's razor. So the idea here is that choosing the smaller number of degrees of freedom is choosing the simpler model, because there are fewer free parameters. Remember that degrees of freedom reflects the number of free parameters, and if we have fewer free parameters, it's easier to explain the model. And smoothing splines are kind of, not necessarily that easy to explain. They're sort of in the middle. They're sort of they're lower, say, on the interpretability scale than least squares or the lasso or some of the other things that we've looked at. Ridge regression. Well, the lasso more. So reducing the number of parameters is worthwhile. So something that has fewer free parameters is an advantage. Okay, so that's pretty much all that I want to say about this. That gets us to local regression. I would like you to go over the math in this as much as you can. I think that there's a problem here that we have different math backgrounds, and so it's not going to be completely obvious whether you can, understand this kind of stuff. But the general form, even if you don't know the math, you should be seeing something familiar about minimizing the deviations. That this represents the sum of some deviations, and you should know generally that RSS, is the residual sum of squares. This is the unexplained variance. And you certainly should know by now leave one out cross-validation and k-fold cross-validation, which is also performed here. Okay, so I'll leave you with that for today, and then tomorrow we'll talk about two different methods, the local regression and general additive models.